Hi, in this video we are gonna verify or actually discuss how can we verify that the solution of the wave equation is given in this form is really a solution of, of the heat equation. Okay, so what we need to do, we have like we always do. How do we verify that something is a solution? We have to find the derivative with respect to time of this guy, and then make sure this is equal to the 2 times derivative with respect to x of the same guy. Okay, so that's what we need to do. So in order to do that, we need to discuss first uh, the term by term differentiation of that infinite sum. When can we do that? Okay, so I'm gonna set up the statements for the theorems we need for series for this to be true. Okay, so let me start with the motivation. Okay, so the motivation is the following. So we're gonna see several theorems or propositions, and before getting into all that, I wanna show you why this is useful. Okay, so using separation of variables, you can prove that the solution of the heat equation is given for of this form. Okay, so how can we verify that? Okay, let's do it. So this is u. So if I take the derivative of u with respect to time, right, uh, u is all these infinite sums, so I'm gonna get derivative with respect to time of u. U is the sum of k n equals 1 to infinity sine n pi x over L e to the minus n pi L squared t. Okay, so the question here is, can I do this? Okay, what is my mathematical basis in order to do this? Okay, so can I interchange the derivative with the sum? Okay, can I do this? Sum n equals 1 to infinity of the derivative with respect to time of all these guys, k to the n sine n pi x over L times e to the minus n pi over L squared t. Okay, once I do that, is this possible? And this is called we call it term by term differentiation. So let me see, term by term differentiation. So let's put it like that. Term, let's put it like, books usually use this, like to use this exactly like this. Term by term differentiation. Can we do this? So we are basically, this is the interchange of the infinite sum with the derivative with respect to time. Okay, so once we know we can do that we don't know right now, we don't know we can do this. Okay, and by the way, engineers do it all the time, so that's a that's a that's a big problem. Okay, so they don't worry about this. Okay, we have to worry because we're the mathematicians. So derivative with respect to time of this kn is just constant, right? Derivative with respect to tan of sine n pi xl is the same because it's constant, right? We don't have time there. Now the derivative of this guy is e to the minus n pi L squared t, because the derivative exponential is the same exponential, times the derivative of the inside. The derivative of the inside is minus n pi L squared, right? This is just chain rule, right? So this is my derivative with respect to time. Now, what will be my derivative with respect to x? 2 times. So I need to check the derivative with respect to time is the same that twice the derivative with respect to x. In order for that to be a solution of that, okay? So remember that this is true, this is valid for finite sum. If I have here finite sum, this is true for superposition principle. But remember, we don't know if that superposition principle is valid in general, okay? Because it's an infinite sum. So you're making a sum infinitely many times, so you don't know how ugly it's gonna get. So if we find the derivative with respect to x, the derivative with respect to x is then the derivative with respect to x, and allow me to skip the sum of all this that we know what is all that is here, right? It's all this. So allow me to don't write it again, please. And then I'm gonna interchange the derivative with the sum. So I'm gonna do sum of the derivative. So I'm interchanging these two. I'm interchanging the derivative with the sum. Okay. So this sum is from n equals 1 to infinity. Right? Sum n equals 1 to infinity. Well, I'm just gonna write it. I'm gonna write it because it's a good memorization. So please, I hope you are taking notes, because that's how you help you to memorize. So this is k to the n sine n pi x over L e to the minus n pi L squared t. So somehow help you to don't be afraid of this terminology. Okay, so then you have k sine n pi x over L e to the minus n pi L squared t. So now we find the derivative with respect to x. So what is gonna be? So this is the question mark here, right? So can we do this? Okay, we're gonna write propositions to see that we can do that. So in that case, this is k to the n, derivative of sine is cosine n pi x L e to the minus n pi L squared t times the derivative of the inside. The derivative of sine is cosine times the derivative of the inside is n pi over L. Okay. Now the next one, we have second derivative of u with respect to x will be derivative with respect to x of the derivative with respect to x, right? That's the second derivative. But I already know the first one, so I already know this one. So the derivative with respect to x of this guy. So this is the derivative of the sum n equals 1 to infinity. K to the n cosine n pi x over L e to the minus n pi L squared t times n pi over L. Right? Now I'm gonna interchange the derivative with the sum. So let me just this time interchange it. So I'm gonna interchange. So sum n equals 1 to infinity of the derivative with respect to x, and this is the question mark, right? Can we interchange the sum with the derivative? So we get this guy, right? And now this is gonna be sum of n equals 1 to infinity, derivative with respect to x. Oh no, sorry, this is gonna find it. So derivative with respect to will be minus sine, no, minus kn sine n pi x over L e to the minus n pi L squared t times the derivative of the inside, so that will be n pi L squared. Okay? So now I compare. So let's compare these two guys. So I'm gonna compare derivative of u with respect to time is this guy. I'm gonna compare it with second derivative. So I'm gonna compare this guy, put in orange. I'm gonna compare it with this guy. This guy is second derivative of u with respect to x. So minus n pi L squared. So check. Okay, so then check. Sine n pi x L, check. E to the minus n pi L squared, check. Okay, so the two things are the same. Okay. So if I can justify that I can interchange the sum with the derivative, that's the way I can verify that this ugly guy, right, that this ugly guy is indeed a solution of my heat equation. Okay, so that justify what I'm gonna do next. I had to give you all these propositions, so you have to. So now you have. Hopefully, you are more willing to recall all these propositions. I'm gonna write for you. Okay, so these propositions can be found on. You can follow useful propositions by Gunther and Lee book. Gunther and Lee. This is on page 58 of that book. Okay, that's in the bibliography. So the first proposition says, it's a very useful one. Oh, okay, so I'm gonna have to give you page 58, and we're gonna start giving you a really useful one that is gonna save you a lot of time, and you're gonna love it. Okay, because once you see how difficult it is to prove uniform convergence, you're gonna love this theorem. This is a theorem. For right now, my favorite mathematician theorem is called the Weierstrass M test. So you can ask me why he is my favorite mathematician. Okay, but in part, this is one reason, not the main reason, but this is one good reason, because he has several results extraordinarily simple that are extremely useful. Okay, so suppose that there are constants m sub n such that g sub n of x is less or equal to m sub n for all x in a set, let's call it S. Okay, and the sum of m sub n is less than infinity. So These m sub n are like your calculus 2. So you have a series that is convergent. Okay. How do you do that? Well, you have your calculus 2. Okay. Then the series sum of gn of x. Well, this is could be n equals to 0 or n equals to 1. It doesn't matter. Whatever it is uniformly convergent on S. Also, it's absolutely convergent. So that means that in the absolute value is also less than infinity. So it's very extraordinary theorem because we are talking about all these series of functions, and this theorem is telling you don't worry about it, don't worry about the convergence. All that you need is your calculus 2 class. You just need your calculus 2. You find a boundary, so you find a series that is bounded for each term of the series, and then that series is going to be uniformly convergent. Remember that what doesn't mean uniformly convergent. So it means you have a function. Well, let's say this is the function you have the function. This is the function you want to approximate. Okay. So S is this set. Okay. It's an interval in this case. S is an interval in this case. So what is uniform convergence? It means you give me an epsilon and you give me kind of this this distance is epsilon. Okay. So you give me an epsilon, and eventually any element of the sum, so any partial sum, so is gonna be here. Okay, so the sum where this is S sub n. So remember, S sub n of x is the partial sum n equals to 0 to n and gn of x. Okay, any part is the partial sum after 1n. All those partial sums are gonna be inside of this epsilon. So that's kind of the convergence you want. Okay, so is very, very, very useful theorem. I love this theorem. You use it a lot in complex analysis because e to the I x, so e to the I x, the norm of this equals 1. Okay, so a lot of things simplify in complex analysis. So this is beautiful. Okay, so now the propositions I'm gonna need is the following. So proposition 1, let G sub n of x be continuous on a set S and and the sum n equals 0 to infinity of g sub n of x be uniformly convergent on S. Okay. So you have two hypotheses. First one, g sub n is continuous on a set S. So we're not talking here about piecewise continuous. No, it has to be continuous on the set S. So something like that, continuous. And this infinite sum is uniformly converging on S. Then that's, so this is 1 and 2. Then the sum g sub n of x n equals 0 to infinity is continuous on S. Okay, yeah, because remember that we were having, if we want to approach this piecewise function, right? So if we are approaching it for sine series or cosine series, the series go like this and go in the middle and then cross it here and then go like that, right? But the limit, at the end, the limit of that series is gonna look like this. It's gonna look like that, point, open, open, and close. That's what's gonna be the limit. So the limit is not gonna be continuous function. Okay, but in this case, my g sub n's are not like this. You know, my g sub n are continuous. Well, in this case, it will be continuous, but they are uniformly convergent. Okay, so this sum is not uniformly convergent. In the case when you are approaching for sine series or cosine series, this not continuous function, the convergence is not uniformly convergent. Otherwise, the infinite sum will be continuous. So the infinite sum for this cosine series is looks like this: tran, tran, tran. So this is, let's call this 2. This is 2. The limit will be 2. But here we are saying, we are talking about uniform convergence. So for that case, my function has to be special. Okay. So here we're talking about, once you know that it's uniformly convergent, your infinite sum is continuous. Okay. How do you prove it's uniformly convergent? You use your beautiful Weierstrass M test. Okay. It's very, very useful. So proposition 2, and we're going to use this, all these results we're going to use when we're proving this result. We want to prove that the solution for the heat equation, the solution for this heat equation is this guy. So in order to prove this, we're going to have to use these propositions, okay? Because we are not engineers, we are going to prove it. We're just not going to leave it there, okay? We have to do all the details. But I'm going to do a little bit for heat equation, and I'm going to do a little bit for wave equation. So it's not too heavy, it's not so much proving, but don't worry, you're gonna have homework, so you'll get it. So let second proposition, let g sub n of x be continuous on the finite interval x between a and b, and let the sum G0 of x be uniformly convergent. On the same interval, right? On AB. Let G2 then be continuous on the finite interval. Let's put it AM interval AB, okay? And let the sum infinite sum G1 of x be uniformly convergent on AB. Okay. Then look at this. We can interchange integration and sum. You have the integral between a and b of g of n x dx. You can interchange a integral ab sum n equals 0 to infinity of g0 of x dx. Okay, so you can interchange these two guys. Okay. This is thanks to uniformly convergence. Pretty awesome. And finally, proposition 3, and then we are ready to prove. We will be ready to prove this heat equation formula. Proposition 3. Let G sub n of x be continuously differentiable on an interval say AB. Well, in this case, probably we have to say on an interval AB. Oh, sorry, open. And assume the following. Well, let's just to save time, let's say interval. And assume the following. And assume the following. First thing, the sum of G and A from n equals 0 to infinity converges at some point A in the interval. Second, the sum of the derivatives is uniformly convergent. Is uniformly convergent on the interval. Then you can find the derivative term by term of the infinite sum you can find the derivative term by term of the infinite sum. That's basically what we want, right? So in this, let me put it like this. So we can interchange the derivative with respect to x with the derivative with respect to x. So we are interchanging the derivative with the sum. Okay. So So yeah, 30 minutes for this. So now we are ready to prove our statement. Okay, that's what we're gonna do.